Pop quiz. You're 10 centimeters from a very long charged wire. If you double your distance, what happens to the electric field? A. Stays the same. B. Halves. C. Quarters. Lock in your answer. Time's up. The correct answer is B. The electric field halves. For a very long charged wire, the field is proportional to 1 over r, so doubling the distance cuts the field in half. So why does the field depend on distance this way? Let's build the formula from scratch. In this video, you'll learn how Gauss's law turns symmetry into a quick electric field formula, and you'll test it with a couple of examples. Before we begin, let's set up the scenario clearly. Imagine the wire is so long it looks infinite and is uniformly charged. Its charge per length is the linear charge density, lambda, in coulombs per meter. With that setup in place, our goal is clear. Find the electric field E at a distance r from the wire. For a positive line charge, the field points straight outward. For a negative line charge, it points inward. To calculate that field, we'll use Gauss's law. It says the total electric flux through a closed surface equals the charge enclosed divided by epsilon naught. But Gauss's law only becomes powerful when we choose the right surface. The trick is to pick a Gaussian surface that matches the symmetry. For an infinite line, the symmetry is cylindrical. Nothing changes if you slide along the wire or rotate around it. So we choose a cylinder coaxial with a wire, radius r, and length L. The wire runs down the center like an axis. On the curved side of that cylinder, the electric field is radial and has the same magnitude everywhere because every point is the same distance r from the wire. On the curved side, the field is radial and the area vector points radial too. So E is parallel to dA. That makes E dot dA equal to E times dA. And the flux through the curved side is E times the area, 2 pi RL. What about the flat end caps? There, the area vectors point along the wire, but the field points sideways, so E dot dA is 0. No flux through the ends. Now find the enclosed charge. A length L of the line contains charge lambda times L, so Q enclosed equals lambda L. Now plug in what we know. The flux through the curved surface is E times 2 pi RL, and the enclosed charge is lambda L. So Gauss's law gives E times 2 pi RL equals lambda L over epsilon naught. Cancel L on both sides and solve for E. E equals lambda over 2 pi epsilon naught r. Notice the key result. The field falls off like 1 over r, not 1 over r squared. So far, we used symmetry to choose a cylindrical surface, computed the flux, found Q enclosed equals lambda L, and solved for E equals lambda over 2 pi epsilon naught r. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Here is one example. Let lambda be 2.0 nanocoulombs per meter and r be 0.10 meters. Plug into E equals lambda divided by 2 pi epsilon naught r. That comes to about 3.6 times 10 to the 2 newtons per coulomb, pointing outward. Second example. You measure E equals 900 newtons per coulomb at r equals 0.050 meters. Solve for lambda. Lambda equals E times 2 pi epsilon naught r. That gives about 2.5 nanocoulombs per meter. Here's a common mistake. Using a spherical surface and expecting a 1 over r squared dependence. Spheres match point charge symmetry. Cylinders match an infinite line of charge. One important clarification. Infinite is an idealization. For a very long but finite wire, This formula is accurate near the middle when r is much smaller than the wire's length. To recap, an infinite line of charge has cylindrical symmetry. Using a coaxial cylinder in Gauss's law gives E equals lambda over 2 pi epsilon naught r. The field points radially and decreases as 1 over r. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.